Hi, I am Amin, and I'm going to present our paper on reasoning about monotonicity in separation logic. First off, let's see why it is interesting and important to reason about monotonicity for program verification. Let us consider the following simple program. This program first allocates a counter and then forks a loop that repeatedly increments the counter. It then proceeds to check that the counter never decreases. It does so by first reading the counter twice and then comparing the value of the first read to the second read. And if the second read is actually smaller than the first read, it will crash. Now, in order to prove that this program is safe, that it doesn't crash, we now need to reason about monotonicity. Let's see how we do this in separation logic. First, let us look at the specification for the counter that we just saw. Our specification is very simple and is only designed for reasoning about monotonicity of the counter. Our specification for creating the counter says that after creating the counter, we get some ghost resources under the name gamma that are used to track the counter. And according to these ghost resources, the value of the counter is at least 0. Now let us look at the interesting operation of the counter reading. If we know that before reading the counter, the value of the counter is at least n, then after reading the counter, we know that the value m that we read is going to be greater than or equal to the value n that we knew previously, and also that the value of the counter after reading it is at least m. As I mentioned earlier, these specifications for our counter are very simple and are only designed to reason about monotonicity. Hence, the specifications for the increment operation are completely trivial. It simply says that the operation preserves monotonicity. All right, given these specifications, let's see how we actually prove that our program does not crash. Initially, we know that the value of the counter is at least 0. This means that after reading the counter for the first time, we know that the value of the counter is going to be some value m that is greater than or equal to 0. And hence, after the second read, we know that the value that we get out of the counter, m prime, is going to be also greater than or equal to the value that we got on the first read. Therefore, our check always succeeds, and we never end up in the crashing branch. Most modern separation logics use partial commutative monoids, or PCMs, to model resources. In this presentation, we're going to focus on iris. A PCM is a very simple structure consisting of a carrier set M, which represents a set of resources, a binary partial operation that is commutative and associative that represents combining resources, and an empty resource, the unit of the monoid structure. For practical purposes, we define our monoid operation as a total operation and instead use a validity predicate to determine when the composition of two resources is valid or invalid. We write that the composition of A and B is invalid whenever A composed with B is undefined. Now, each PCM gives rise to an extension order. In the extension order, A is less than B if there exists some resource C such that B is equal to A composed with C. A very simple example of a PCM is the monoid of natural numbers together with maximum as the operation and 0 as the unit of this operation. In this simple monoid, the extension order simply coincides with the less than or equal order on natural numbers. We embed resources in our logic by including a proposition in our logic, own A, that asserts ownership of A. Here, gamma is the name of the resource. The PCM operation now in the logic represents the separating conjunction, in the sense that owning A combined with B is the same as owning A and owning B. One important fact about resources in Iris is that there is a global metatheoretical invariant on all of Iris that all resources owned in the system at all times must always be valid. This means that whenever we own some resource, we know that that resource is valid. Furthermore, we can only allocate resources if we know that those resources are valid. The update modality models how we update and allocate resources. Intuitively, the proposition update P holds whenever P holds after updating resources. Now, if we own some resource A, we can update it to some other element B of the PCM if we have that A frame-preservingly updates to B. The frame-preserving update basically says that we are not invalidating the global invariant that I mentioned before. That is, by updating from A to B, we are not invalidating other resources in the system. A very important PCM in Iris for reasoning about programs is the so-called authoritative PCM. Given a PCM M, the authoritative PCM auth M essentially consists of two kinds of elements, the full part and the fragment. And the idea is that the full part keeps track of the total information that we have in the system about our resource, while the fragments track a lower bound on the information that we have. As these intuitions indicate, since the full part is going to track the total information in the system, we cannot have two full parts in a system at the same time. The combination of two full parts is invalid. On the other hand, if we know that a full part combined with a fragment is valid, then we know that the fragment must actually be smaller in the extension order than the full part. Composition of fragments in the system is simply composing the underlying elements. Now, the frame-preserving update for the PCM auth M depends on the exact M. We'll see some examples of that. The crucial point is that the authoritative PCM allows us to use the extension order of the underlying monoid in our reasoning. Now let's see how we actually define those predicates that we use in our specification of the monotone counter. For this purpose, we simply use the authoritative PCM over the PCM of natural numbers that we saw before. The isCounter predicate is then a simple invariant that says the value of the counter is always some natural number n that we are tracking as the exact value of the counter in ghost resources. And counter at least predicate is basically saying that we have a fragment with value m. Now, if we put these two pieces of information together, we get that if we have that the value of the counter is exactly n, and it is at least m, it must be that m is less than n. This basically comes from the property of authoritative PCM that owning the full part and the fragment means that the elements are in the extension order, and the fact that the extension order on the PCM of natural numbers is just the order on natural numbers. Notice that the only frame-preserving updates that we can have with this authoritative PCM is going to be compatible with the order on natural numbers, because decreasing the value of the full part of the PCM is going to invalidate other fragments that might possibly be in the system. Our main contribution in this work is constructing the PCM called monotone R. Given a pre-order relation on a set A, we define a PCM monotone R and an injection from A to our PCM. Two values, x and y, are related by R if and only if their injection into the monotone PCM is related by the extension order. This means that just like we did with the counter, we can now reason about monotonicity with respect to the relation R using the authoritative PCM over the PCM monotone R. Notice that we can update our resource only if it is compatible with the relation R. Furthermore, we know that if we have the full part and the fragment part, they are suitably related by the relation R. An observation that we can make is that if the relation R that we start with is a joint semilattice, that is, it has least upper bounds of any pair of elements, and also it has a bottom or least element, then R is already a PCM. We can simply take the join operation as the operation of the PCM and the bottom or least element as the unit of the PCM. Furthermore, we can take our injection to be the identity function. Now we can observe that if X is related to Y in our PCM, then it must be the case by definition that there exists some Z such that Y is equal to the join of X and Z. But this is the same as having X is related to Y in R. Our general construction monotone R is essentially then the free completion of the relation that we get to a joint semilattice structure with a least element. Please see our paper for the details of construction and for the details of why this construction is a canonical construction. Okay, let us look at a few examples. The first example that we look at is the example of general monotonic references. The idea is that given a relation on values, we can construct a monotone reference that can only be updated with respect to that relation. Here we take the relation to be a relation on some arbitrary set A and assume that we have an injection, a partial function that injects from values into A. Given this information, we can define the following. We can say that the value tracked in the resource name gamma is at least value V if we know that the value V is in the relation and that we know that we have the fragment of the element X that represents this value in the order. Similarly, we can say that the value tracked in resource gamma is exactly value V if we know that value V is represented in our relation with an element X, and that we know that the exact value tracked in resources is X. We define the monotone points to relation for our monotone references as owning the ordinary points to relation for the reference, and also knowing that the value tracked in resources is exactly V. Okay, let's look at the properties of these references. First of all, given a reference L with value V, such that V is represented in our relation, we can always create a monotone reference. If we know the value of a monotone reference, we can always take a snapshot of this value and know that the value of this monotone reference is never going to decrease. If we know that the monotone reference has some value V, and we know that the value of this monotone reference is at least W, then we know that V and W are related. When we read a monotone reference, we simply get the value of the reference as is expected. However, when we want to update the value of a monotone reference, we need to show that the value that we are updating the reference to is actually greater than the value that is currently stored in the reference in the relation R. Finally, just as we created a monotone reference out of an ordinary reference, given a monotone reference, we can deconstruct the reference and get back our ordinary reference, and also know that if at some later point in time, we come back with some value that is greater than or equal to the value at the time of cancellation, we can recover our monotone reference. Let us look at another simple example. Let's consider the following program, which allocates two references, X and Y, with the initial value 0. It then launches two threads. The first thread writes 1 to X and reads Y. The second thread writes the value 1 into Y and reads X. Now this program may return 0, 1, or 1, 0, or 1, 1, but it will never return 0 and 0. And the reason for that is that if this program returns 0 and 0, it means that both reads of X and Y have happened before both writes to X and Y. And that is impossible because each thread is first performing its own write and then performing its read. In order to reason about this program, we look at the graph of the history of how these values X and Y can evolve. The values can be 0 and 0, and then they can be updated to 1, 0, or 0, 1, and then subsequently to 1, 1. In order to prove that this program never returns the pair 0, 0, we use the authoritative PCM over the monotone PCM on the reachability relation of this graph. And we define two predicates, exact state and observed state, using the full part and the fragment part of the authoritative PCM respectively. And the idea is that if we know that the exact state is S and we have observed some state S prime, then the exact state, current state S, should be reachable from the state that we have observed S prime. We use a very simple invariant for this program, which says that there exists some state S such that the value of X and Y are determined according to the state, and also this state is the exact state tracked in resources. We then verify the two threads under this invariant. For the left thread, if the return value is 0, then we must have observed the state 1, 0 here. And if the return value is 1, then we have observed one of the two final states. On the other hand, for the second thread, if the return value is 0, then we must have observed the state 0, 1. And otherwise, we are in one of the two final states. Now, if both threads return 0, it means that we have that the state that we are currently in, the state that is tracked in the invariant, must be some state that is reachable from both the states 1, 0 and 0, 1. But that is impossible in our graph. Therefore, such execution cannot exist. Let us look at our final example of using the monotone PCM, reasoning about causal consistency of distributed databases. Let event 0 and event 1 be two events in our system such that event 1 depends on event 0. We want to prove that the following program does not crash. This program waits for the event 1 to be observed in the system and then asks whether event 0 is also observed. Because event 1 depends on event 0, if we have observed event 1, we must have also observed event 0. Therefore, this program should not crash. Now, in order to prove that this program does not crash, we need to reason about causal consistency of our database. Let's see how we can do that. In order to reason about causal consistency of our database, we define the following causally closed subset relation. We say that E is a causally closed subset of F if E is a subset of F, and for any events EV and EV prime in F, that EV depends on EV prime and EV prime is in E, then EV is also in E. We use the authoritative PCM over the causally closed subset relation to define our resource. We define two predicates again, observed full and observed fragment, that track the set of observed events as is expected from the PCM. If we know that the full set of events is E and the fragment is E prime, then we know that E prime is a causally closed subset of E. Let's see how we use this to actually prove that our program does not crash? We use a very simple invariant that says that there is a set of events that describes the contents of the database. This set of events is causally consistent, and this set of events is the set that we are tracking in our resources. The isObserved function checks whether an event is observed or not. The specification says that if before checking if some event is observed, we know that the set of observed events is at least E, then we know after the check that the set of observed events is some greater set F, that is a superset of the set E that we started with, and that the return value is a Boolean value. It is true if the event that we check is actually in the set F, and it is false if the event that we check is not in the set F. All right, let's see how this specification allows us to prove that the program does not crash. Well, after waiting for event EV1, we know that we have observed some set of events E1 that includes EV1. Now, if we check whether the event EV0 is observed or not, then we get that there must exist some set of events EV2 that is a superset of EV1 that we have observed. And this function, according to this specification, returns true if the event is actually if event E0 is in E2 and false otherwise. Now, since EV1 is in event set E1, we know that it is also in event set E2. But then since E2 is a causally closed subset of the set that we are tracking in our invariant, and we know that this set is causally consistent, and we know that E1 depends on E0, we know that E0 must also be in E2. Therefore, this check can never return false, and hence the crashing branch is unreachable. With this, let me conclude this talk. I will mention that please take a look at our paper for the exact construction of the monotone PCM, and also for the discussion of why this construction is a canonical construction, as in it arises as a free functor. Also see our paper for details of the examples that I presented and how also the reasoning principles that I used in this talk for reasoning about causal consistency are exactly the same that we have used in our POPL paper that is going to be presented later this week. So if you're interested, please also take a look at that talk. Finally, all the results that I presented are formalized in Coq and are available online. Thanks for your attention.